Okay. Let me see. Okay. Can people hear? People can hear me over the recording, over the mic system, right? So that's hooked up. Okay. Let's get started first. Let's put on the magic transparent mask. Okay. So what I'd like to start off with is I'll talk about homework 4 in a minute, but I think I'd like to start with the daily problem. The daily problem, again, we started talking about backtracking. Are there any questions about backtracking from last time? Just generically, not the homework, but just the methods. Okay, so the key notion, remember, was that with backtracking, we were representing our solution by coming up with basically 3 different functions. If I remember correctly, we had to specify a solution vector A, and we had to come up with 3 different functions, which was like testing basically, is A a solution? We had to construct candidates. And we had to process a solution. That was the solution. Those were the kind of ways to use backtracking for this. And I think that this how you divide the work among these functions gets to be have some interesting consequences, and I want you to take a look at it here. The problem for today is daily problem is about trying to find a derangement. What is a derangement? A derangement is a permutation of the numbers 1 through n such that no element is in its right spot. Namely, that the ith element of the permutation is not equal to I. Can anyone give me a derangement on 4 items, just to make sure we understand it? A derangement from the items 1 to 4. Yeah?
4, 3, 2, 1.
4, 3, 2, 1 is a derangement because every element is not in its right spot. Okay? So let's go now. Can someone give me a way to construct all derangements, write about this backtracking program to construct derangements by basically telling me what is a solution going to be? How do you test when you've got a solution? When you've filled up the array. Construct candidates, given that you've filled in this many slots, what are the choices for the next spot? And then process solution, what do you do when the backtracking thing says it has an answer? Does anyone have a way to construct derangements? Yeah?
Or is a solution part, you could just check if the...
So first of all, which problem are you basing this on? I showed last time how to do it for subsets and permutations. Which way are you basing this on? Permutations, okay, because obviously a derangement is a permutation. So now, what are you telling me that the breakdown is?
So for is a solution function, you could just check if the vector that you're working with, the size is equivalent to n.
Have I filled up my solution vector? You're going to be making a vector like this, and you want to know when you fill it. So is it a solution? That I guessed was just basically is k equal to n. That's what you're telling me. Just like the permutation one. Have we filled the array? Okay. What about construct candidates? What are the candidates for if I have put down a 4 and a 3? What are the candidates for the next spot? How are you going to do that?
For that, what I did is I do a loop from 1 to n plus n to n inclusive.
Yeah.
And then I just check that, is the I not equal to the length of the vector size I have, minus 1, and I is not already in the vector.
Okay, so what you're saying is the candidates here are going to be the numbers 1, 2, 3, 4, except for any one that has appeared before it, ka-chunk, ka-chunk, except for, which is what we did before for permutations, right? And except for what the index of the slot is. That would rule out 3, but 3's already been ruled out, right? And the candidates here are going to be 1 or 2. Okay? Any questions? So his idea is he's going to go find anything that could possibly be in a legal derangement, okay, and put it there. Okay, and that means it can't be anything that occurred in the early part of the matrix of the solution, and it can't be I if we're filling the ith spot. Okay? And any questions about that? Okay, and what is process solution going to be?
What I did is I added all the valid derangement permutations into a bigger list.
Okay, you're saying you wanted to have a list of all the derangements for you to look at and admire forever. You're going to put them in some kind of an array. Now that I don't think is a great idea. Okay, why is that? Well, one thing to note is, how many derangements are there as a function of n? The answer is probably a lot. Okay? And if you're storing all solutions, notice that you can sometimes generate all solutions, but you can't store anything. If you want your program to do more work, you can always have it run longer. But the moment you run out of memory, you get a crash, right? So you could, if it's a small number, if n is small, you could store the derangements and look at them. More likely you're going to want to print them out and get them out of your system, or count them, or do something like that. Okay? But do I believe that what he's going to do is going to end up with an array of all the derangements? Yes. Any questions about this solution? Is there another way that we could have done this? Is there another way we could have constructed all derangements? Okay, then doing it the way that he did, by dividing the work up differently among is a solution, construct candidates, and process solution. Does anyone see a different way to do it? Well, I see a different way to do it. What would it happen if is a solution is going to stay the same? For construct candidates, what if I construct all permutations? Okay? Meaning I worry about what has happened before, but I don't worry about, I don't worry about whether the ith element is in I. Right? Does everybody agree that would just generate all permutations? And then I could go to process solution and instead check if a sub I is not equal to I, for all I, print the permutation. You see what I could do? I could construct all permutations and then at the end throw out the ones that are not derangements. Once I have a permutation, check if it's a derangement and throw it out. Does everybody agree that that is also a correct solution? Which solution is better? Okay. Which one looks like it should be better? Let's go back and do it. You see what the distinction is? He is checking to make sure that he never puts an element in its own spot. Whereas I am very happy to put a 1 in the first spot, build all permutations that start with 1, and throw them all out at the end. Right? Which method is better? You should have an opinion on this. Okay? Yes. What? You like the first one better. Why do you like the first one better? Okay, you're saying that I am doing a lot of extra work, it looks like, because I am constructing solutions that can't possibly help me. Does everybody see? The moment I put a 1 down, everything I do from then on cannot possibly help me. Okay? So mine is going to take time proportional to order n factorial. Yours is going to take time proportional to the number of derangements. Does that kind of make sense? Okay. So this makes this solution look better. Is it really better? Well, it turns out, does anybody know how many derangements there are of n items? If you had taken a good enough combinatorics class, I don't know if 301 is a good enough combinatorics class, the number of derangements turns out to be n factorial over e, where e is 2.718. Okay? And if you know this, which one of the two items is better? If we know that the number of derangements is n factorial over e, which one of these is better in a big O sense? Or are they the same? Does everybody see that they're really just the same? What this is saying is that it turns out that 1 out of every 3 permutations is a derangement. So if you take something that is constructs all permutations, or just constructs the number of derangements, there's only a factor of 3 difference there. And it isn't the kind of thing that I'd normally worry about. Okay? So knowing that I know that, I'll say they're about the same. But which is the one that should be right and the one that you should be much happier with? I would say it is the red one. Because that's clearly the smarter one. You're never constructing something that you don't need. Okay? In general, this is the idea of pruning, which is what's going to make a big difference on your homework 4, is that pruning out a bad solution early is going to be important because there's very, very few subsets of subsets that realize the optimal set cover, while there's a huge number of possible solutions. So you don't want to construct all possible solutions. You want to just construct the ones that have a chance to help you out. Any questions about this? Any understanding one way or another? Okay, good. Let me go move on here. So before I go any further into pruning, I just want to talk about the, if I can, let me see if I can do something here. Let me talk about the homework problem again. Okay, hold on. Am I frozen? Uh-oh. Bad things seem to be happening here. Is this possible? Hold on. Okay, the right thing is happening. I just have to erase all this. Okay, fair enough. Okay, so remember that the assignment that you have for homework 4 is to solve the backtrack problem, is to solve the set cover problem, excuse me. And the input is, you are given, what is this now? This is bad. Now we're in big trouble. Sorry, now I'm in hopelessly big trouble. Okay. Is that working? Okay, good. Okay, you're given as input a collection of subsets. You have a universal set of n items. Here, these are the 12 dots. So in this example, n equals 12. You are given various subsets of those dots as input. If we numbered the dots 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then The blue subset correspond to what? It was called 4, 5, 7, and 8. This orange one corresponded to 2 and 8. Okay, this one was 1 and... Wait, no. This one was, the orange one was 2 and 5. This red one was 1 and 4. You get the idea. And the goal was that we needed, given this list of subsets that we had, I could construct all of them if people are confused. We wanted to find what's the smallest number of subsets. Here, 3 subsets have the property that they cover all the elements. And that's what your goal is, to find the fewest subsets you need from the input to cover all the elements. Any questions about what the set cover problem is? Okay? Your job is going to be to write a backtracking program to take the input set cover problem and, write a, write a backtracking program that implicitly tries all 2 to the m subsets of subsets, and then checks whether it creates a cover. If it creates a cover and it has fewer subsets in it than the best one I already know of that's a cover, keep it. If not, move on. If you do it in a really brute force way, construct all possible subsets of subsets, then check if it's a cover. It's going to take something like that time to check for a cover. You would have an algorithm and a program that will satisfy homework 4. Okay? But it will be slow. My claim is if you write a good program here, you will not have to try all 2 to the m possible solutions. Okay? By pruning the search and backtracking, you will be able to avoid constructing most of the subsets. Any questions? Okay, we'll talk a little bit about pruning today, but that's kind of what I need you to do here. Any questions? Okay. Now, some people, when they heard this problem, again on Piazza, said, what if I use a faster computer than somebody else? This is going to take, the goal is you have to come up with you're given an input case, you have a minute of computer time to solve the problem. Does it matter if you use a very fast computer or your cell phone? Not really, because, we're doing an exponential search here. What you guys are going to discover when you write your programs is on a small example, it goes instantly. On a slightly larger example, it goes instantly. On a slightly larger example, it goes instantly. On a slightly larger example, it stops and dies. Okay? It seemingly takes forever. It's going to hit a wall. And whether the computer is fast or not, it just slightly changes where you're going to hit that wall. Okay? The winning program is going to be millions of times faster than the slowest program in this class. Okay? That's why I don't worry about you using a faster computer. And that's why some of you said, I'm going to use a parallel machine. I'm going to use all those threads and I'm going to get it. And again, maybe you've got 64 processors on your machine. I don't know what you use as your laptop. Your program may run 64 times faster. 64 times faster is uninteresting, okay? Making it, it's not terrible, but I mean, that's not going to really change the picture here. How you do the pruning is going to make a difference. Any questions? Okay, so we're going to have to talk a little bit more about pruning here. Okay, any questions? So let me just look at the rules for the, sorry about this. I'm having a tough time. For some reason today, I'm having a tough time navigating here. So what are the rules? This is an assignment you do without your partner. Everybody's got to write their own program. Okay? you'd better make sure you know what I mean by a set cover. Discuss it in Piazza, discuss it with me, discuss it with a TA. If you don't know what you're trying to do, you can't possibly do it. You're going to have, there are a lot of test cases I give you, okay? You should start with the small ones and work your way up until you hit a wall. Because if you start with the biggest one, your program is just simply going to go into vapor lock and not come back with anything. Okay? Any questions? And our goal here is, I want the fastest program that gives a correct answer. Correct answer means a minimum size cover. Not one that's kind of close, but I need the exact best. Some people here want to use heuristics and say, oh, I can come close to the exact cover in a few seconds. Am I great? And I'd say, no, you're wrong. Okay, we need something that always gives you the exact optimal answer. Okay, and you want it to be as fast as you can. Any questions? And again, I'm going to have you run it on your machine. I want to know how big an example you can solve in 1 minute or less of you sitting there watching it. Any questions? Okay. And we will eventually have a contest among the fastest programs. But for now, I encourage you, if you're confused by backtracking, get a simple backtrack program working first before you go and do anything else. Okay? Any questions? So again, my recommendations for you are first, like I say, keep it simple. Okay? Start with a simple backtracking program to do it, and make sure you can generate all subsets and test. If you can do that, then you've got a working program and you're way ahead of the game. Then I want you to try to make it faster. Okay, but I want you to start with something simple, especially if you're confused. Now, what should you be worrying about? One thing is, it's clear that what your real goal is going to be is to prune the tree. We're going to talk about pruning today. But your goal is to not construct all 2 to the n subsets. Your goal is to stop your search and your work as quickly as you can. Some of you saw that, like when we talked about the daily problem. You very much want the first of the derangement programs. You don't want to consider any candidates to extend a solution if that solution cannot possibly help you. Okay, that's what pruning the tree means. Okay, and I need to see you, that's where the money is. Sometimes you have people who say, oh, I'm going to write it in assembly language, or I'm going to delete the comments, or I'm going to use iteration instead of recursion, and think that's going to be faster. Don't mess with this kind of stuff. The key is, how do you prune the tree effectively? And that's best done at a high level. Any questions? Finally, the last bit of advice that I will give you is, once you have your program pruning done as best as you can, okay, what I'm going to want you to do is, there are tools available for your favorite programming language called profilers. And these are tools that, given a program, and you run a run of the program, will count up how much time the program spent in every line of code that you have. Okay? So, depending upon what your favorite language is, you'll have your own profiler tool. But this is useful because what I will tell you is, at the end, you will find that 90% of the time in your program is spent in 2 or 3 lines of it. And you probably don't know which 2 or 3 lines until you have that computational analysis. So first, do the pruning. Get the pruning as good as you can, okay, because that's where the real savings is. And if you prune later, it's going to change what those 2 or 3 lines are that it's spending most of its time in, okay? But there are tools to do this that you probably should get some familiarity with. Any questions? Any questions about the homework assignment? Okay, has anybody got a working program for the homework 4? I'm seeing one person twitch. How far big an example can you do? You just did simple backtracking, and did you run it? And how far does it go? You ran the first one, and it ran to completion, and you felt good about yourself. Okay, you didn't hit a wall. Did you go further to see it hit a wall? That's an instructive thing. So take your simple program, run it on. You will see at some point it's going to hit a wall and not go any further. Okay? And that's kind of the benchmark for the baseline for you trying to build a better solution. Any questions? Okay, let me talk now about techniques for pruning. Okay. Pruning is, as I said, is how you cleverly look at a problem and figure out how to avoid doing more search than is necessary. And the classic, puzzle for doing that is something called the 8 queens problem, which I'm imagining many of you have seen. Now, in chess, what can a queen do? A queen is the most powerful piece in chess, and it can move anywhere along a column, can move anywhere along its row, it can move anywhere along a diagonal. Kabunk, kabunk. So this queen over here can attack any of the squares that I drew on those lines. Okay? The 8 queens problem says, given that I have an 8x8 chessboard, how many queens can I put down so that no 2 queens attack each other? Okay? This is an example, if you look at it, where I have 8 queens and no 2 of them attack each other. Could I put 9 queens on an 8x8 chessboard and have them not attack each other? No. Why can't I have 9 queens? Yeah?
Well, if you think about it, let's say that the queens all attack horizontally, and if you have 8 of them placed already in a way such that they don't interfere with place in life, it's going to have to be interfering.
Okay, I think the mask I'm having trouble with hearing, but I think what I'm hearing is that every queen has got to be in a row. You can't have 2 queens in the same row, or else they would attack each other. And if you have 9 queens, by the pigeonhole property, you're going to have at least 2 queens that are going to be in the same row and attack each other. So you can't put down more than 8 queens. This proves that you can put down 8 queens. What are all the configurations that such that you can put down 8 queens? Okay, and you can imagine writing a program for doing that by backtracking. Okay, any questions? Let's think about that problem. What is the way that we should write an 8 queens program? And just like with the, the derangements thing, there are different ways you could do it. Okay? What is the representation of the solution that you want to write? How can we represent a solution to an 8 queens problem? Does anybody have any proposals? Yes? You want to say you could have, what I'm going to say, 8 row and column pairs. So you're going to have the numbers, we're going to have 8 row and column pairs where they've got x1, y1, x2, y2, ... Does everybody see that that's a possible solution? This queen is in position 1, 3. This queen is in position 2, 5, and so on. Are there any other possible ways of representing a solution to the 8 queens problem? Yes?
You don't need to do pairs. You could also just do like a regular array, and then the index represents like the column, and the number represents the...
Okay, I'm officially declaring your mask is too thick. Okay, so let me ask you not somebody else. Okay, what's your answer?
You can do like 2 ways. So you can do it in you can do it like in a 2D array.
Okay, in a 2D array. So I think what you're saying is another solution might be that we have what I think what you're telling me, correct me if I'm wrong, is a solution. Oh, God damn it. Hopeless. What happened here? Okay, don't know exactly what happened, but it was bad. Okay, let's go back here again. Let's come down. Sorry about that. Sorry about this a lot. Where am I? Okay, so one solution, as we said, was what I'm going to call 8 pairs. And these are pairs. The other solution that I think you were just suggesting is an array that is basically of length 64. And for each one, it's going to tell us yes or no. Each one of these things is going to be a flag to tell us, does the, is there a queen at that square? Okay? You're basically numbering it as being square 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, ... And what you're going to be saying is, the 6th one is going to be a yes. The other ones were no's before it, right? That's the representation you're looking at, right? Now what was your representation? Try again.
Use like an array of size 8, and then the index represents like the row number or column number, and then the value inside just represents the corresponding coordinate.
Okay, what he's saying is you can get away, instead of listing each pair, notice that if you've got an 8 queen solution, there's got to be a queen in every single row. Okay? So what is that argument? Let the ith column represent the row, and we'll have the value in here be the column of the queen. So here in the first row, the column was a 3. In the second row, the column was a 5. In the third row, the column was a 2. Does everybody see that kind of representation? Because we know by being clever, every row can only have one queen in it. Instead of storing the pairs explicitly, we can store them, just store the column associated with each row. Any question? Now, which of these 3 representations is best? Which of them is worst? Okay? I would think in general, how do you judge? I think the one that has the fewest number of states to go through is the one that is best. Let's take a look at this one where we had a bit vector of size true and false. How many different values are there going to be of that bit vector? 64 things. Each square either has something or doesn't. How many solutions does that have? Okay, there's different ways to count, but yeah? You're saying 2 to the 64. What do you say? You would say the same thing. I will say that you could be that. There's another way you could look at it, though. You could say it's 8, choose 64, because all the other ones are going to be false, except you're picking 8 true ones, right? This is a one way that might be, but I agree with you that if you're going through all, oh God darn it, what happened here? Gone. Having a lot of problems today, people. Let's come back here. I'm not sure I know why this is happening, but I'm having more trouble. This trouble I haven't had as so much in the past. So we agree that one way was 2 to the 64. What was the pairs thing? In general, without thinking about it very much, you had 8 pairs, each of which was a square represented, right? You had 8 times 8. You had 8 choices for this, 8 choices for that, and you were doing this 8 times. What does that mean? That should mean basically 8 times 8 to the 8. Why? I've got 8 choices for this one, 8 choices for that one. There's 8 times 8 ways I can fill in each square, and there are 8 of these squares. These squares. This is how many solutions that is. How does this compare to 2 to the 64? Well, what is this going to be? This, I claim, is 2 to the 3 times 2 to the 3. What is 2 to the 3 times 2 to the 3? What is 2 to the 3 times 2 to the 3? 2 to the 6. What's 2 to the 6th raised to the 8th? Okay, that is going to be 2 to the 48. Does everybody agree this is wildly smaller than it was the bit vector thing, but it's still a large number? What about the third representation, where we had 8 vectors, things, each of which was going to be a column, which was going to go from 1 to 8? How many possible solutions to that were there? What was it? 8 to the 8. What is 8 to the 8? Okay, we think about it as a 2 to the something. That would be what? That would be 2 to the 3. Okay, if it's 8 to the 8, what is that going to be? 8 to the 8 is the same as 2 to the, what you call it? Right, 2 to the 3 to the 8 is 2 to the 24. How does 2 to the 24 compare to 2 to the 48? Is it half as big? No. It's unbelievably smaller. This is the important thing to see here. You're dealing with exponentials now. The exponent got cut in half. But cutting the exponent in half changes the size of this problem humongously, right? So this is a much tighter representation, and that is what we kind of want from this. Any questions about that? Let's go back to the slides now and hope I can make it stick. I'm sorry that this seems to be on a hair trigger today. Let's go down. So this is basically saying what I did now. Actually, is it 8 to the 8 or is it less than that? Notice that there's actually less than 8 to the 8. Why is that? Notice the first spot, if I had my 8 to the 8 solution, 1, 2, 3, 4, 5, 6, 7, 8. Suppose I put my first queen in the first spot. What are my choices for the second spot? Yeah? It's clear I can't put another queen in the first spot again. Why? Because that means that they're in the same column and they'll attack each other, right? So really what I need is actually not 8 to the 8 solutions, but 8 factorial solutions. If I, just by using that observation alone, I'm down to 8 to the 8. 8 factorial. 8 factorial is only 40,000. 40,000 things, or how many things you guys could go through by hand in, I don't know if I should lock you in a room and make you try, but going through 40,000 solutions is not something that really should unbelievably scare you. Okay? It's not something I want to do, to be perfectly honest with you. But 40,000 solutions is almost hand size now. Okay? Any questions about that? Okay. So if we're going to use this vector representation, now we know that what we're going to do is put the queen in the first row, second row, third row, fourth row, ... What are the candidates for the next row? If I put down my queen, what should be my candidates? Okay, let's go back to my picture here. Sorry, hopefully this is good. Suppose I put down this queen and that queen. What are the possible places I could put a queen on the third row? Can I put it over in the first thing? Let's make it here. Can I put it here? Yes. Can I put it here? Yes. Can I put it here? No. No, no. Can I put it here? No. Can I put it here? Yes. Can I put it here? No. Does everybody agree that what I need to do is to now go through, for my next spot, I'm going to say what spots in my array are consistent with the queens already there, right? And the hope is that I'm not going to have to choose between, I had 8 choices here, 7 choices there. I should have 6 choices. Notice I only really have 3 choices. My construct candidate should now prune the set of possibilities I put down as much as possible. Okay? And then once I put it down, let's say I decided to make this my queen. What choices do I have for the next spot if I put my queen in the first row? Not there, not there, here, not there, here. I guess I can put it here. No, yes, and yes. Okay? Any questions about that? How do I implement this? Here is my code. The key thing is the construct candidates routine. Given that I have put down I have an input solution A, which is just going to list the queen in each column, and I filled k spots of them out of ultimately n, what are my candidates going to be? My candidate should be a number between 1 through n, because those are my columns. Okay? Once I do that, what am I going to do? I'm going to say that a move in that legal I is a position I is a fair candidate to put something if no existing queen is going to attack me, what am I going to do? I'm going to check all of my k queens so far. Notice this goes up to k. Okay, I'm going to check all of my k queens and ask, does the jth queen, okay, which is in position A of, basically A of j, does that queen attack me j rows down? Well, it will attack me diagonally if the difference of the rows, the difference between j and k, okay, I mean the column, the jth column, and the queen that's in the kth column, okay, if, okay, my queen is positioned, okay, j positions from me, okay, again, notice what is the threat condition? When is there a diagonal threat? Maybe it's easier to go back to look at the example again. Why is this queen a diagonal threat for that square? It is because the difference in the value of the column, the second column, minus the fifth column, is the same as the absolute value of the difference between the number of rows that we have here. Okay? It's because the difference from here to here is the same as the distance from here to here. If you see that, that's exactly what I am doing in this code. This is the condition for testing whether there is a diagonal threat. Much easier is a column threat. If I am going to put, I want to put my queen in the ith column, but the jth queen is already in the ith column, then the ith column is not a legal move. If position I survives the challenge for all k queens, then I is a legal candidate, and I'm going to add it to my list. I is as a candidate, and the number of candidates gets bumped up by 1. Okay? And this is the heart of the 8-queen solution. Any questions about what we're doing here? We're coming up with all columns that survive, okay, on, basically the jth row. Okay, all columns that survive on the kth row, okay, based on the k queens that are above it. Any questions? Okay. And when you do that, okay, what is the rest of the routine? Well, the rest of the program is actually quite easy. Okay. When do I have a solution? I have a solution when I put queens in every row. So when k is equal to n. And what am I going to do when I have a solution? He wants to store them. I may just want to count them to know how many of them there are. Okay? And if I count them right, I can get away, in some sense it's just faster like that. Any questions? Depends what I want to do. And if I do it that way, this is the main program. Initially I have 0 solutions. I'm going to call backtrack on an initially empty solution vector, and eventually it will tell me how many things you can count for. And again, I was able to run it when I did on a tiny machine. In a few minutes I could get all the solutions for a 14 by 14 board. Okay? And probably you can do even better. Any questions? Okay. Any questions of how the 8-queen solution works? Okay. And this idea of finding the tightest possible solution space and then letting construct candidates only pick the ones that can possibly help me, that's what's called pruning. And that's the key to getting this be successful. Any questions? Okay. Here is another problem where I once used backtracking. This is one of the war stories in the book, and what I'm kind of proud of, is this question of how do you, how do you put pieces down on a chessboard so every single square is under attack. Okay? This is a problem that was originally asked in 1849, but no one actually, when I was a grad student, nobody knew for sure what the answer was. In this particular example, I don't know if anybody knows about what the chess moves are. There is exactly one square on the board here that is not under attack. Can anybody find which square here is not being attacked? I mean, again, we can pick a random thing, ka-chunk. What's attacking that square? The king, right? Ka-chunk. What's attacking that square? A knight. Let's pick some place in the desert here. What is this one being attacked by? The bishop. My claim is on this board there is exactly one square that is not being attacked. Does anybody see which one it is? Okay. I claim that there is one square on the board that is not being threatened, one safe place to be. This is one of the problems when it's a rainy day because there's fewer people to find it quickly. Who's got one? Which square is not being threatened? Anyone? I claim it is this one. Okay, nobody is taking out that knight. Does everybody kind of see that? Okay. So this is a configuration that has the property that you take the 8 main pieces in chess, you can arrange them on a chessboard so that, that 63 out of 64 squares are threatened. It's a reasonable question to ask, is there a way to make it so that all 64 are threatened? Okay? And people asked this question, like I said, first time in 1849. Nobody had found one that could threaten all 64 squares. Suppose we wanted to write a backtracking program to go through all the solutions here. How should we do it so that it's relatively efficient? First, what should my solution vector be? People see what my problem is? I want to put down 8 different pieces, okay? A king, a queen, 2 rooks, 2 knights, 2 bishops, okay? Such that every square on the board is threatened. Okay? What should my solution vector be? Any idea? How should I represent a solution? Yeah?
Can you do something similar to the previous one, but instead of only storing the column, but you also attach like a type, the piece type that you're placing?
Okay. You're saying, can I do what I did before? And again, it's clear that there can be many solute pieces in the same column. So it's no longer going to be the case that I'm going to have 1 piece per column or 1 piece per row, right? So I can't get away with a solution vector quite that small. How can I represent what my solution vector is? Does anybody have an idea? Okay, yeah.
I'm thinking of like the maximum amount that can be in a single row. That's 8, right? Like 8 pieces can be in a single row. Is that possible?
8 pieces can be in a single row, that's true. You want to say, so one thing you could do, again, is to use a 64 element array where we're numbering the squares 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? You say two coordinates. Notice that your 8 by 8 coordinates I can just represent by a number from 1 to 64, right? So I find that easier to think about. I've got 64 squares. One possibility is for each square, I now write down king, queen, rook, bishop, knight, or blank, right? That would be one possible solution, vector. Do you agree?
Yeah, did you want another one?
What would you, yeah, what's another one?
I thought if it was the row, 1 by 8, but you have pairs of king and both, that type of column.
One, you now have to have 8 things, and what do you want each one of the things to be?
Type and column.
You want it to be type, king, and the column, okay? Well, the king is in which column now? This is the king, right? The king is in column 5. I claim it's not enough to know what column the king is in. You probably need the column and the row. Okay? Because each king, we no longer have the nice property that we only had one piece per row or column. Okay? So I think we got to specify that. Okay? So if we believe that, you're really going to be telling me you want to have 8 pieces. The first one, for each piece, you're going to tell me what the name of the piece is and what the square is, which is an 8 by 8 thing, or 64 choices. Right? So you're having something, a vector that somehow got 8 records. Each record's got a piece and a number from 1 to 64. Is there a slightly better way to do that? Yeah.
You could have it so that each index represents a piece, and then the value is just the column.
What if we say that there is a king column, a queen column, a rook, rook, bishop, bishop, knight, knight, and now we just have the number from 1 to 64 of where that piece is. Okay? The index positions will tell you the piece type. The value in there will be the, the square that it's on. Right? How many solutions of this type are there? How big is our search space? The search space is all the things we might have to go through. How big is that search space going to be? Yeah? Okay, I'm hearing 64 factorial. Okay. Oh, what you're trying to say is no 2 pieces can be on the same square. Okay? If no 2 pieces are going to be on the same square, what you're telling me is it's going to be 64 times 63 times 62, right? The choices I have for each slot depend upon what I've had before. You're giving me something like 64 factorial over what, 64 minus 8? 56? Okay? That's what I'm hearing you say. Okay? Any questions about that? Okay? That's roughly the size of my thing. Is there any way I could make that space smaller? So I like the fact that he's trying to reduce the solution space by not letting me put down a number more than, once. That does make the thing smaller. Okay? Instead of it being 64 to the 8th, it's 64 times 63 times 62. It's a little smaller. Is there anything else that I can do to reduce the size of my search space? Okay? Again, the goal here has got to be I don't want to search any configuration more than I have to. Does anybody have any ideas? One idea that you can use is symmetry. Okay, let's go back and look at this thing. So again, we're going to want to do this kind of backtracking and thing. We're going to want to count how many configurations there are. This is basically what you were saying about the size of it. And you get a number that's something like 10 to the 15th. Now, I am happy searching through about 10 to the 8th configurations on a computer in a few minutes. 10 to the 15th is a big number. I've got to get that number down if I'm going to be able to do a good job here. What other ideas can I use to reduce the search space? One important idea is symmetry. What is symmetry? I'd like to note that some of these configurations, my goal is to find this unicorn of a position, one that where all 64 squares are covered. If I have a chessboard and I rotate it 188 degrees, are more or less pieces covered, squares covered, or is it the exact same amount? It's got to be the exact same amount, right? Does everybody see that there are symmetries where the same configuration of pieces can occur in a couple of different ways that really aren't different configurations? One example would be, again, I said if I turn the board around 180 degrees. Another one would be to note that, that a chessboard is symmetric around its axis, around its main diagonal. If I put every piece that was over here, if I put a piece that was over here, over there, and a piece that was here, over there, and a piece that was here, over there, do you see that I could reflect the pieces? Okay? And everything is still going to attack everything else. The attacking relations are not going to be changed. Okay? The same thing is true if I divide the chessboard in half. If I put a piece that was here over here, if I do that for all the pieces, they swap the side of the board, but everything still attacks everything else. It's the exact same configuration. There are a lot of different symmetries here. I'd like it if I could do my search so that I never got into, I don't construct the same solution multiple times. Does everybody see what I'm trying to do? There is one, maybe a unicorn position. If I find one, I know that I can construct others by these reflections. How can I avoid searching all of those symmetries? What if I take a piece that was unique on the board, like let's say the king, the queen, it could be the queen, it could be the king, and I limit the queen to these squares? Does anybody see that if I have any solution to this problem where the queen is not in one of these squares? Suppose you said, no, the queen is over here. Well, what does that mean? That is the same thing as a queen that was here that was reflected over there, right? What if you say, no, the queen was over here? That was the same as this one, reflected around the main diagonal. In fact, with a little thought, you should be able to see that if you put limit the queen to only these 10 positions, any solution to that will attack all 64 squares can be reflected into a solution that will have the queen in one of these squares. And if that's true, instead of having 64 choices for my queen. I only really have 10. And that observation alone is enough to cut the search space by a factor of 6. Any questions? Okay. In fact, there's a slightly better way to do it. That if you allow the queen to be anywhere in here and restrict the bishop to the white bishop to a certain set of half the squares, you will still see all configurations. But it'll be even smaller. But I think that the 6 queens thing, the 10 queens thing, should be obvious to people. Any questions? What is then going to be, if we do that, it's now down, my search configuration is down to 10 to the 12th. What should I now do to further prune the search? Okay? In a backtracking thing, what are we going to do? We're going to say that we're going to have our first choice was a king and a queen, and what do you say? Maybe it was a knight and a knight and a bishop and a bishop and a rook and a rook. Does it matter what order I put the pieces down? Recognize, what do I want to do to prune this? I want to say if I put my king in square 36 and my queen in square 23 and my knight in square 7 and this knight in square 13, it would be great if I could now prove that there was no way to finish the job. Okay? My goal here is to try to find a solution that covers all 64 squares, or equivalently prove that it doesn't exist. The quicker I can make a decision that this partial solution will not help me, okay, that it can't be extended into a better solution, the better off I am. Right? How would I stop my search? If I could prove that this so far could not be extended into a winning solution, I would have construct candidates for the next part return an empty solution. If there's no choices for the next spot, then I would go to the next candidate on the previous level. How can I argue, if I have a partial solution, how can I prove that there's no way it will lead to a full solution? Can anybody think of a way that if I put down, let's go back to this example over here. How would we be able to argue, maybe, that I put down these pieces so far, that there is no way to put down bishops, okay, to finish covering all the squares? That's what the pruning is, right? If I can argue that there is no solution from this partial solution, what criteria can I use for that? Yeah? You're saying I need to be able to show that I can't cover all the squares that remain with my 2 bishops, right? How can I quickly come to a test to say that there is no way to cover all the squares left with my 2 bishops? What if I knew the maximum number of squares that a piece could threaten? How many pieces can a knight threaten? What is the number of squares that a knight can threaten? Yeah? 8. I can go ka-chunk, 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 ka-chunk. So a knight can threaten 8. How many pieces can a king threaten? How many pieces can a king threaten? Yeah? 8 is also. So the king and the knight equals 8. How many pieces can a, let's take a look at a queen threaten. Let me try to make this down. What is the number of pieces that we could hold, that a queen could threaten? What's the maximum? I'm going to guess that the queen probably in the center of the board can do the most damage, right? It can threaten 8, can threaten 8, it can threaten, what is this? It looks like it can threaten 8, 8, 8, and what is this? 7. Am I right? Okay, actually it's not 8, excuse me, take that back, it's not right. There's 8 in my first row. Then once I've got it, how many can this guy threaten? He can threaten 1, 2, 3, 4, 5, 6, 7, 8. This one's now threatened. Now this can do 9, 10, 11, 12, 13, 14, 15. I think it is 8, 7, 7, and 7, and 6. Okay, you have to count that. Okay, what does that add up to? That adds up to 13 plus 15 or 28. My claim is, when I counted this carefully, queens can only threaten 27 squares. I'm pretty sure I repeated. There's one square that appeared in all the rows and columns. I had to subtract that out. A queen can tackle 27 squares. A rook can take on 14 squares. What is a condition to prune a partial solution? Suppose I have put down a solution, partial solution, where I have these pieces down, and so far they have covered a total of 40 squares. And if I look at the positions that remain, okay, let's say that what I haven't put down was a knight, and a king. Sorry. Okay. What are my choices here? A knight can protect 8. A knight can attack 8. A king can attack 8. Does everybody see that I can only cover 24 more squares in the best of all possible worlds with these last 3 pieces? If I've got 40 squares covered so far, is there a chance that I'm going to be able to finish? Yeah, because I've got, that adds up 40 plus 24 equals 64. But if I only had 39 squares covered, does everybody see that I'm doomed? At this point, the power of what I have left is less than the power I need to finish the job. And does everybody see this gives me a pruning criteria? If I get lucky, if my positions here were not in an order where they covered a lot of squares, it might be that there's not much work to finish the job up. Okay, that I might be able to prune it without putting down as many as 3 more pieces. Any questions about that? If you believe that, any questions? If you believe that, in my solution vector, what is the order that I should put the pieces down? Does it matter if I put the pieces down king, queen, rook, rook, bishop, bishop, knight, knight, or maybe the reverse of it? Does it make any difference? Yeah? My goal is, you're saying that if I put the larger pieces down, okay, what I want to do is to be able to prune as quickly as possible. If my last piece was a queen, I would say, hey, there's a chance that my queen could cover 27 squares. Okay? It's pretty hard for you to put down 7 pieces and still have 27 squares to remain, and so I'm going to have to go through it. If the last pieces I'm putting down are my weakest ones, I'm more likely to get a pruning. I'm more likely to be able to say, look, you've put down these pieces, you've only covered 39 squares, you don't have enough firepower to cover the rest, give up. Okay? And that is the pruning that we need to be able to do. And when we did this, we eliminated 95% of the search space when we ordered the pieces by decreasing mobility. Any questions about how that worked? Okay? Once we did that, that got us, it looked like sort of in range to do this. Okay? In fact, it was still, computers were very slow back when I was in grad school. And it still, that program would still have taken us about 1,000 days to run on the crummy computer we had back then. But by coming up with other pruning ideas, okay, we were eventually able to do this in 1 day's worth of computing. Okay? And that's kind of the moral that I guess I'd like to leave you with, that you can fight the combinatorial explosion by systematically looking and arranging your search so that you maximize the chances that you can stop looking at this configuration. And know that if I cut my search now, I am not going to make my, I'm still going to end up with an optimal solution. Okay, but going further from this partial solution can't help me. Any questions? Any questions about backtracking or the assignment or anything like that? Okay, if not, I'm going to thank you for your attention. Oh yes, question.
How did you prove that no solution exists?
How can I prove that there's no solution? Well, again, I think that what I said there was really a proof. If you have a vector of possible pieces, these pieces are down, and they cover 39 squares, and the maximum squares I could hope to cover, okay, with a king, a knight, and a knight. The most squares I could possibly threaten are 8, 8, and 8. The total number of squares that could hope to be threatened is going to be 39 plus 24, which is 63, right? No matter what I do with this, there is no way I can cover enough squares for this to cover all 64, right? You have a similar issue in your set cover program. Wouldn't it be great if you have put down, you had a solution vector, you said, I'm including this subset, and this subset, and this subset, and this subset. And the best I could possibly do to finish it is going to have a solution of size 7, but I already have a solution of size 6. If the best I can do is going to be 7 or better, and I already have a solution of size 6, should I continue to explore here? This is a dead end. Okay? And that's exactly what you want to do on your homework. Any questions?